Welcome to another episode of Mr. Avila Physics. Today we're going to be talking about work. Now, usually the word work has a different meaning depending on what you are discussing. But in physics, work has a very specific meaning. And this word is used to describe what happens when a force acts on an object over a certain displacement. So, in physics, we define work as the product of the magnitude of the displacement times the component of the force parallel to that displacement. So, what does this mean? It means that in order for work to happen, a force needs to act on an object, and that object needs to move due to that force. Okay? So the work done by a force is equal to the product of the magnitude of the displacement times the component parallel to the displacement. In other words, we would have that work is equal to the magnitude of the displacement and times the component parallel to the displacement, where this angle, theta, is the angle between the force and the displacement. So if we look at this again and we see it here on this picture, then here we have a person moving a crate using a force F. But this force is not completely parallel to the displacement, which is completely horizontal. So we need to use the horizontal component of F that is parallel to the displacement, right? Therefore, the work done by this person will be equal to the force used to cause the displacement times the displacement. All right, okay. So let's look at an example. You push a loaded grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart. So you have a cart, right? And you apply a horizontal force of 30 newtons. And the cart moves a distance or a displacement of 50 meters. Now, here the displacement is in this direction. The force is also in this direction. So the force and the displacement are parallel, which means that the angle between the force and the displacement is 0. So cosine 0 is equal to 1. Therefore, the work done would be equal to force times distance, which is 1500 newtons meter of work. Now notice here that the unit of work is the Newton meter, but there's a special name given to this unit, which is the joule. All right. Now, work deals with two vector quantities, which is force and displacement. But work itself is a scalar quantity, right? Which means that work can be positive or negative, but you don't have a specific direction. Okay? So if the force and the displacement are parallel, then this would be positive work. If the force and the displacement are in the same direction, then we have positive work. If the force and the displacement are in anti-parallel directions, then we would have negative work. All right, now, is it possible to exert a force on an object and do no work? Of course it is, right? we just said that work is equal to the work done by a force is equal to the magnitude of that force times the displacement of that object. If there is no displacement, then there is no work done. You can push against a wall all day long and the wall will not move, so you are not doing any work on the wall. Another example would be, consider that you're holding a heavy bag of groceries in your hand. You're applying a vertical force, right? You're applying this force right here, but the bag is not moving. Therefore, the work done by you on the bag is 0. Okay? Now, we can see this in 2 different ways. One way is seeing that the displacement is 0, so we can find out that work is equal to force times displacement. So if this is 0, then work is equal to force cosine theta times 0, which gives me 0 joules. Another way of saying this is that if this person was to move, this person would move in this direction. So the angle between the force and the displacement is 90 degrees, which means that we would have work is equal to Fd cosine theta, Fd cosine of 90 degrees, and cosine of 90 degrees is equal to 0, so work is equal to 0 joules. Well, then we can say that when a force is perpendicular to the displacement, then that force does no work. Well, what if you are moving? Then the same case. You do no work on the bag of groceries because the displacement is not being caused by the force that you are applying on the bag, right? The angle here between force and displacement is still 90 degrees, and cosine 90 degrees is still 0, okay? So, when a force is perpendicular to the displacement, no work is being done by that force. Now, in the case that you wanted to lift the bag of groceries above your head, then yes, then you would be doing work on the bag. So if you were to move the bag of groceries from here to here, then yes, it would be applying a vertical force. The displacement would also be vertical, so you would be doing work on the bag. But if the bag is kept this way and the displacement is horizontal, then you do no work on the bag. All right, let's try this example here. You have a person that pulls a 50-kilogram crate 40 meters along a horizontal floor by a constant force of 100 newtons, which acts at an angle of 37 degrees as shown. The floor is rough and it exerts a frictional force of 50 newtons. Determine the work done by each force and the net work acting on the crate. Pause the video here, take a couple of minutes, and see if you can come up with an answer. All right, welcome back. So, this is the case where we have, okay, here we have our crate. Oh, here we have a force that is equal to 100 newtons acting at an angle of 37 degrees. We have friction force acting in the opposite direction, and the box moves a distance of 40 meters. So let's see if we can find this out. Okay. All right, so the first question is asking us to find the work done by each force. So let's start with F. So the work done by F is going to be equal to F times D cosine theta. So the force is 100 newtons, the displacement is 40 meters, and the angle between the force and the displacement is 37 degrees. So I could say that this is going to be equal to 100 times 40 times cosine of 37, which is positive 3194.54 joules. Now, let's look at the work done by friction. And let's use a different color here. It doesn't work very well. All right, so the work done by friction is going to be equal to force times distance times cosine theta. Friction is 50 newtons. The displacement is still 40 meters, but the angle between friction and the displacement is 180. So since friction acts in the opposite direction of the displacement, then this is going to be negative, right? And this is going to be negative 2000 joules. All right, and then question B is asking us to find the net work. Now, to find the net work, we have two different methods of doing that. Our first method is to find the work done by the individual forces and add them. So our net work is going to be equal to the work done by F plus the work done by friction. This is going to be equal to 3194.54 plus negative 2000. This is going to be equal to 104.54 joules. Our second method to find net work is to find the net force and multiply the net force that is parallel to the displacement and multiplied by the displacement. In this case, our net force is going to be equal to Fx minus friction force times the displacement. This is going to be equal to 100 cosine of 37 minus 50 times our displacement, and this gives me 100 times cosine of 37 minus 50 times 40. That gives me exactly the same answer, 1194.54 joules. So whichever method you want to use, it's the same. All right, let's look at this example. Determine the work a hiker must do on a 15-kilogram backpack in order to carry it up a hill of height 10 meters as shown. Also determine the work done by gravity on the backpack and the net work on the backpack. And just to make things simpler, let's assume that the hiker moves at constant velocity. So there is no acceleration here. All right, pause the video here, take a couple of minutes and see if we can come up with an answer for this. All right, welcome back. Let's see what we can do on this example here. All right, so here we see that the hiker is lifting a 15-kilogram backpack to carry up the hill, right? So that means that the force that the hiker is applying on the backpack is vertical, right? This is the force the hiker applies on the backpack. The displacement is up the hill, right? So the angle between the force and the displacement is this right here, okay? This is theta, okay? And gravity acts on the backpack in this downward direction, okay? The displacement is still up the hill, which means that the angle between the force of gravity and the displacement is this one right here, 180 minus theta. So let's see what we can do. So the work the hiker must do, let's just write it down here. So work is going to be equal to FD cosine theta. The force that the hiker must use is equal to the weight of the backpack, right? So the weight of the backpack is going to be equal to mg, and then d cosine theta, okay, if we look at this triangle right here, then, oops, I erased the whole thing. So the work of the hiker is going to be equal to FD cosine theta, which is mg d cosine theta, right? If we look at our diagram, okay, and we look at our ramp, so if I make a triangle here, then this is also theta and this is h, right? Which means that d cosine theta is equal to h. So this right here, this is h, which means that the work done by the hiker is equal to mgh, right? We have all the information, so the work done by the hiker is going to be equal to m 15 times 9.8 times 10, that would be 1470 joules. All right, now let's look at the work done by gravity. So the work done by gravity is going to be equal to FD cosine theta. So this is going to be equal to F, which is the force of gravity, which is mg. And then this is going to be equal to D cosine of 180 minus theta, right? Because this is the angle, this 180 minus theta is the angle between the force of gravity and the displacement. But we also know that cosine of 180 minus theta is negative cosine of theta, which means that this becomes mg d minus cosine theta. So this becomes minus mgh, which is minus 1470 joules. So it looks like the hiker and gravity are doing the exact same amount of work, but with different signs, which means that the net work done by gravity will be equal to, the net work done on the backpack will be 0 joules, because, well, this is what happens. All right. Cool. All right, so up until now, we've talked about constant forces, right? But sometimes the force that we apply on an object is not constant. For example, as the rocket moves away from Earth, the force of gravity changes, it becomes weaker as you get farther and farther away from Earth. So the force of gravity would not be constant. Another example is when you stretch or compress a spring, right? The more you compress it or the more you stretch it, the harder it becomes. So the force is also not constant. So how do we apply our formula of FD cosine theta if the force is not constant? Well, let's look at this, okay? So to do that, we would graph the component of the force that's doing the work through the distance. So if it's not constant, we would have something like this, right? Now, if we approximate this line as a straight line, then what happens if I try and find the area underneath this graph? Well, this is a triangle, so the area of a triangle would be equal to 1/2 base times height. So this would be 1/2 base, which is distance, and height, which is force. So this would be equal to work, right? Because this is force times distance. Area 2 would be the area of a rectangle, which is base times height, which would be distance times force, which would be FD, which is also work. So it looks like in order to find the work done by a varying force, then all we have to do is find the area underneath the curve between those 2 points. We're going to see more examples about a varying force in later videos. All right. Thank you all for watching. See you next time.